Hey guys, welcome to the Aeromechanics of Solid class. This is Professor Nehru, Department of Aerospace Engineering, Essence College of Technology. And today we are going to see about the unsymmetrical bending, and that we are going to see unsymmetrical bending of the beam. So let's we go to the. So the topic is pure bending. The bending is very several from form of stresses of structure. The simple bending theory applies when bending takes place about an axis which is perpendicular to the plane of symmetry. Bending moment acts along the axis of member. And let us take this ABC beam, which is arbitrary in shape, where the moment is applied in M and M dash, in A and B point. And let us have some assumption to solve the pure bending equation. The normal plane remains normal when and after bending, even after bending. So there is no net internal axial force acting in the beam. Stress varies linearly over the cross section. Zero stress exists at the center, and line of center is in the neutral axis, right? So here we have the neutral axis acting in the neutral plane in the cross section area, and the momentum m and m dash acting in the x-axis. If you see the cut section of this area, the centroidal line, the neutral axis line, is passes to the area, and the neutral point, the bending stress is zero, and the maximum will be top sigma max, and the minimum will be at the mid, and bottom it also maximum. So distribution, stress distribution is shown in the figure. So both stress and strain is having maximum at the top and the minimum at the neutral axis. So bending stress and strain at the point may be computed as sigma by sigma max is equal to y by c, and y is the distance and c is the central point. And unsymmetrical bending assumption, the plane and before and after it will be remaining the same. Let us take this diagram where arbitrary area and xyz is a location, and load is applied as a torsional load p, and shear for s6 axis y is acting. Internal forces to be calculated in the cross section at any point, and it is cutted in here somewhere, and we are getting the clockwise and anti-clockwise load to be concentrated compromised by P and P, and mx my is acted, and the external load is acting in the system. So the product moment of area, our second moment of area, we'll call it as ixx iyy. So from the parallel axis and perpendicular axis theorem, the second moment of area of the surface about x and y is defined as ixx is equal to integral of x squared dA, and iy will be integral of x squared dA. Similarly, the product moment of inertia of the section will be ixx equal to integral of xy into dA. So since the second cross section of the most structural member to be used, bending application consists of combination of rectangle and the value of product second moment of area. For such section is determined by the addition of ixx value for the rectangle section. So let us take in a rectangular cross section where it is taking the first quadrant. So all the x and y, I mean that is a k and h location are positive. So we'll calculate the cross section area in BA. Ix will be A h into k. So determining the principal axis location for the given cross section. Let us take this the normal axis and the principal axis, whereas UU and VV be the principal coincide central axis, and the XXY will be the orthogonal axis. Alpha will be the angle between the both principal coordinate central axis and the orthogonal axis, right? So to find IUV equals summation of UV, the delta A equals 0. But the definition IXX and IUU, IYY, IUXY, we replacing in the principal axis IUU, IVV, IUV. So here we have summation of y square at dA. This is for IXX. For IYY, summation of x square dA. IYY it is summation of xy into dA. Whereas for the principal axis IUU equal to summation of v square dA. IVV equal to u square dA, and IU will be UV dA. The relationship between this orthogonal coordinate and the principal axis coordinate. So xy comma u coordinate represent as u equal to a plus b plus db equal to the area x cos alpha plus y sin alpha. Whereas alpha is principal plane axis angle, and v equal to gp minus hgp. We will call it a y cos alpha minus sin x sin alpha. So here we are finding the IU as summation of y cos alpha minus x sin alpha the whole square dA. So by expanding this equation, cos square alpha summation of y square dA plus sin square alpha summation of x square and dA minus 2 sin alpha cos alpha summation of x y into dA. So we are getting the final equation for IU is equal to cos square alpha into IXS plus sin square alpha into IY minus sin 2 alpha into x. Similarly, for IVV equal to cos square alpha IYY plus sin square alpha IXX plus sin square sin 2 alpha IYY. So IUV we call it as cos square alpha into IYY IXY minus sin square alpha into IXY minus sin 2 cos IXX minus IYY. So here we are going to find out when it is acting in the principal plane, then IUV equal to 0. So tan 2 alpha is equal to 2 IXY minus IXX minus IYY. So cos square alpha is equal to 1 plus cos 2 alpha by 2. Sin square alpha is equal to 1 minus cos 2 alpha by 2. So IUV plus IVV we call it as IXS plus IY by 2 plus IYY IXS minus IY by 2 cos 2 alpha minus IXY sin 2 alpha. So similarly, we'll get the angle, the principal plane angle. We can solve here. Sin 2 alpha and cos 2 alpha. We read it as minus IXY root of IXS minus IY by 2 the whole square plus IXY the whole square. Similarly, cos 2 alpha will be write it as IXS minus my IY by root of IXS minus IY by 2 the whole square minus plus IXY the whole square. So you are getting IXS IYY and that is IU IVV we call it as without the angle, and we are getting this in terms of the amount of inertia and x-axis for the orthogonal. So this is for the small distribution, such distribution which is acting directly to the cross section. Neutral axis passes to the O point, and the cross section of A is area. For any arbitrary area delta A, the location x and y, the bending stress sigma is equal to E load by R. So we call the sigma z equal to integral of sigma a dA equal to EP by rho r dA. We replacing the integral of P a dA equals 0. So P equal to x sin alpha plus sin y cos alpha. Sigma is equal to E by r x sin alpha plus y cos alpha. So mx moment acting in the beam, integral of sigma z y dA, my equal to sigma z x. By replacing this uh, ixx iy and sigma x, mx will be replaced as e sin alpha by r integral of xy dA plus e cos alpha r by integral of y square dA. So if you find mx my, finally we will rewritten this bending stress equation sigma is equal to mx bar by ix into y plus my bar by y into x. So whereas mx bar and my bar are the combination of my minus mx ix divided by y into whole divided by 1 minus ix xy whole square divided by ix is iy. Similarly, my y bar is equal to my minus mx into I xy by ix whole divided by I 1 minus ix whole square divided by ix is iy. So this is the equation where we'll get the sigma is equal to mx by ix by into y plus my by y into x. So these things we are recollecting the pure bending and the direct stresses and principal stresses, and how to solve the pure bending equation. So we'll see in the next class. Thank you.